Hi everyone! This will be another video in our AP Physics C series, which we are not affiliated with and do not own. This will be part 1 in our rotation videos, and I will be focusing on moment of inertia. Before we actually get into moment of inertia, there's a few things that we need to know. Obviously, something everyone should know by now is F equals ma, sigma F to be exact equals ma. Another thing is torque is going to be the cross product between F and R. And if you didn't know, this cross product is sine theta between F and R. If you are unsure on what torque is conceptually or how to use it or how to find it, I would come back to this video, maybe visit our future torque videos, which will be coming soon, because it's pretty integral to learning moment of inertia. Another thing you need to know is the relationships between acceleration and rotational acceleration, or alpha. Here we have linear acceleration, here we have alpha. So A is going to be alpha times the radius involved in a scenario. Now you can see the relationship between this and this equation right here, where linear velocity is going to be the radius times angular velocity. So to fully understand moment of inertia, first we're going to derive the formula. So in this situation, we have an object, this red ball right over here, and it's moving in circular motion around an axis, or what we call the fulcrum at the center. So I showed the fulcrum through this triangle right here. So try the questions I'm asking you on your own, and then maybe pause and then see if they're matching up with mine. So first we're going to write the sigma F statement in the y direction. So our sign convention is going to be up and to the right as positive. This is y and this is x. So in the y direction, as you can see, we have this force F right here. So we're going to say it's this sigma here, F equals ma in the y direction. Now we're going to write out the torques that are acting on this ball. So since this is the F is going to be the force, and R right here is going to be the radius, we're just going to do F xr, or FR sine theta. Now theta in this case is going to be 90 degrees, and sine of 90 degrees is just 1. So torque equals FR. Now we're going to try and combine these equations. So our next step is just going to be rewriting these in a way that they can be connected. So torque right here is going to be describing the rotational motion of this red ball right here. But the sigma F statement is going to be describing the linear motion at a certain point in time. So in order to relate these, they need to have some sort of bridge between them. So we're going to take this statement right here and turn it into this. Because as we know, this relationship exists, so now we're just using it. Now, as we derived right here, torque is going to be FR. So if you take torque equals FR, and we just got an equation for F right here, its torque is going to be MRA R, or MR squared alpha. Sorry, I said A, but I meant to say alpha. So this is going to be our equation for some sigma torque. As you can see, if sigma F equals ma, and sigma of torque is mr squared a, you can say these accelerations are similar, but this is what we call the moment of inertia, as it is a multiplier to the acceleration, the angular acceleration. Now, this multiplier, you can see it in action here. The kinetic energy, the rotational kinetic energy formula is actually 1/2 moment of inertia, or I, times rotational velocity squared, or angular velocity squared. And as we know, our linear kinetic energy is just 1/2 mv squared. So once again, you can see these velocities, whether angular or linear, are lining up with the same power, and we have the same coefficient in front. So once again, these multipliers are lining up, which is why moment of inertia exists. Now, moment of inertia is going to be sigma mr squared, meaning it is scalar and there will be no negatives or positives involved when you're solving for it. If in a system there are multiple moments of inertia, you always just add them together to get the total moment of inertia in that system. If you're experiencing a system pretty much beyond point charges, or that's not that simple, you will have to use an integral for it, which is what I will cover in the next few examples. And that will be r squared dm, because the r that you're using in moment inertia, like for example here, is not small enough to be dr. But what can be broken up is dm into small pieces, and infinitesimally small pieces. Now, let's take a point mass scenario. Here we have an m, a ball of m on each side, and they're both a distance L from the fulcrum. So here, the moment of inertia on this ball would be ml squared. Now the moment of inertia on this ball would also be ml squared. So if we have I equals sigma mr squared, it would just equal ml squared of this ball plus ml squared of this ball. And that's just going to be 2ml squared. So these simple problems will be on the AP test, especially in the multiple choice part of the AP test. So it's nice to just have these quick skills under your belt to get them out of the way so you can focus on the harder questions, which will start looking like this. So here we have a meter stick, and this fulcrum is at one edge of this meter stick. So if we were to use I equals sigma mr squared in this scenario, it would not work, because you can't just take this entire m of the meter stick and say it's a distance r from the fulcrum. You need to take these infinitesimally small dm's, which are all going to be a different distance r. See, this dm is a distance r1. Now this dm over here is a distance r2 from the fulcrum, which is much longer than r1, which is why we cannot use this. Instead, we will have to use an integral, and the integral will be r squared dm, because as you saw here, this dm can be infinitesimally small, but these r's will never be infinitesimally small. I mean, they can be infinitesimally small, but at least in this scenario, it's definitely something that is not. So another thing about this problem will be that we will be calling r x. So here we'll call this s equals x squared dm. And there'll be a reason for this later on that you will probably find out in like 2 minutes. Actually, like 1 minute. So the next part of this is that we don't have dm. Like, how you can't say that because we need bounds for this integral, you can't say that dm can go from 0 to m. How would that work? You want it to go from things that we have, and we have our distance r. So it would be better for our bounds to go from 0 to r, which means we want to get our dm in terms of r, or now we're calling it x. So how can we do that? This is where we bring in something called density, and specifically linear mass density for this example, but not necessarily for every example. So our linear mass density will be lambda, and lambda is going to be mass over length. Now, in this scenario, and this is really important to note, density is actually uniform. And this means for any combination of mass and proportionate length in this scenario, lambda will always be the same. So m over L is going to have the same lambda value as dm over dx. So now we can get dm in terms of dx. So dm equals lambda dx. And we can put that back into our integral. So now we have I equals the integral of x squared lambda dx. And these, as we were talking about before, our bounds are going to go from 0 to r, or now I'm going to be calling it L for less confusion, L. So now we go on with our integral. It's not that complicated. Lambda here is density, so it's going to, and I just said it's uniform, so it's going to be a constant. So we can pull that out of our integral, and it can just be from 0 to L of x squared dx. And it's nice how these match up, because that's otherwise the integral wouldn't work. And then we have lambda equals 1/3 x cubed from L to 0, from 0 to L. And if we go about that, sorry, no equation there. Now you may be thinking, what do we do with this lambda? If you go back to when we first defined it, you see that it's m over L of the entire meter stick, which are both variables that we know and are given. So we can put this back into the equation as m over L times 1/3 L cubed, which in turn is going to give us 1/3 ml squared. And that's our final answer. So you can notice that it's not just 1/2 ml squared for every scenario. In this case, it was 1/3 ml squared, which is why it's so important to use the integral. And for our last example, we'll be using a cylinder that is rotating about its central axis. So here we have said cylinder. Sorry, it's a little thick. I'm going to say it's going to be rotating this way upon its central axis. It's going to have a radius of r0 and a height of h. So you may be thinking, in this scenario, we broke it up into little dm's, which are all a different distance away from the fulcrum. But in this case, how could we do that? How could we do dm's, like this way, or that, or this way? See, that none of those would work, because it is a 3D object that is rotating about its center, which actually lies within the object. None of those would work. So for this, we would have to use concentric shells. So think of this cylinder as a paper towel roll. So these shells are basically going to be one roll of paper towels in this huge roll. So this little shell right here is going to have thickness dr because it is infinitesimally small, and we have to add up all these little shells, the moment of inertia of all these little shells. And it's also going to have a mass of dm because, once again, it is infinitesimally small. So if we go back to our integral, I equals r squared dm, we cannot use lambda in this scenario. Because how would we use... Okay, we cannot use lambda in this scenario. And why is that? Lambda, as we saw before, is going to be mass over length. But in this case, which length would be relevant to our shells? Would it be would it be dr or our radius right here? It would not be, because our shells have another dimension to them, which is height. Which is why we will use rho, which is going to be our volumetric mass density, which is going to be, so it's going to be m over v. So that's going to turn into mass over the volume of a cylinder, which is going to be pi r0 squared h. And once again, another thing to star, this density in this case is uniform, which means we can turn it into dm over dv. Now, we need to change this dm. Oop, not there. I meant we need to change this dm in this integral right here. So we need to get dm in terms of dv. But what is dv? Our dv, as any v has to be, is going to be length times width times height, but not of the entire cylinder, but only the shell. So if we take the shell, it's hollow on the inside, hollow. This is just one paper towel that's curved around. It's not the entire shell. We take this shell right here and we unfold it. So you rip the paper towel and you unfold it. It's going to have dimensions of 2 pi r, which was the circumference, the height of h still, and a thickness of dr, which is what we discussed before. So now our length is going to be h, our width is going to be 2 pi r, and our thickness is going to be dr. So rearranging this for it to look better, 2 pi r h dr is going to be dv. Now we can find our rho again. So m over v equals dm over dv, which equals dm over 2 pi r h dr. Now to get dm out of this equation, we can make dm equal rho 2 pi r h dr. Now let's plug this back into our integral. So I equals r squared dm, which now equals r squared pi 2 pi r h dr. And now we can have our bounds from 0 to r naught. See how the integral can become, well, obviously it doesn't look that pretty right now, but now we have real bounds that we can actually use. So another tip is, like, you always want to look for which bounds you can actually use. What are you given? What would be easiest to work with? And go about getting your variables in a manner that you can actually use those bounds. So back to this. Now all we have to do is simplify and solve. So we can take out constants and combine variables. So 2 is a constant, pi is a constant, and since it is uniform, rho is a constant, and h is also a constant. So we can pull this out, 2 pi rho h, integral from 0 to r naught, and these terms are the same, so they can combine, so that's r cubed dr. So from here, the integral is pretty easy. 2 pi rho h, and then we have 1/4 r to the 4th from 0 to r naught. And since we have 0, this is just going to be 2 pi rho h times 1/4 r naught to the 4th. Now, simplifying this further, because we can't just leave our rho here. If we go back, our rho actually was m over pi r naught squared h. So let's put that back in the equation and simplify. So 2 pi, so instead of rho, we're going to put what we derived for rho, times h times 1/4 r naught to the 4th. And simplifying this, we're going to have pi cancel out, we're going to have h cancel out, we're going to have this turn into 1/2, and we're going to have this turn into r naught squared. So it's going to be 1/2 m r naught squared. Now don't be fooled that this looks exactly like the equation. This was derived differently, and in any case, this mr squared is usually the same, but this coefficient doesn't have to be, but it can be different, so be careful. And don't always assume that it's going to be 1/2 mr squared. That is all for now. Drop any questions in the comment section below. Smash the like button, and see you hopefully next week. Bye!